Swayam Prabha. Digital India. Educated India.
Okay, good morning, good afternoon. Welcome back to the series of lectures we've been having on analysis and design of rigid pavements. We actually have finished 30 out of 40 lectures, so actually 75% of the way through, and we learned a lot, I think, so far. So, as a brief overview of the many concepts we learned, we had basically 4 modules. In module 1, we learned, it was an introductory module, we learned different aspects of rigid pavements, we learned types of rigid pavements, JPCP, JRCP, PCP, CRCP. I mentioned there that JRCP is rarely used and PCP is a very specialized application, so we don't talk about it in this series of lectures. JPCP is of course by far the single most used type of rigid pavements. CRCP is also used a fair bit. And so we mainly focused, as I said then, on JPCP and CRCP. Although if you've been following around the lectures, it might feel as though I've only been talking about CRCP so far. But there's a very good reason for that, which I will talk about actually in today's lecture. So today's lecture is actually going to be devoted exclusively to CRCP, probably our first and not last, we'll have one more for Indian practice, but one of only 2 lectures which is devoted exclusively to CRCP. But the real reason, as we shall see today, is that at least at the analysis level, design level is a little different, but at the analysis level, JPCP and CRCP are almost identical to each other. So that's why we don't really do any special discussion on CRCP. Whatever we learn for JPCP largely applies to a very large extent to CRCP also. Okay, so module 2 and module 3, we actually went about learning analysis of rigid pavements. So you may wonder why, if the course is called analysis and design of rigid pavements, why do we spend 2 whole modules? That's about half the class on analysis. It's because in our modern mechanistic empirical principle of design, we actually design is iterative analysis. So in our mechanistic empirical principles of design, we actually start with a trial section. We have to calculate some distresses, and there are sophisticated ways to do those. That's what we've been talking about all this time. We calculate some distresses, we apply certain reliability. We'll talk about reliability in the next lecture. We apply some amount of reliability, and then we compare the predicted distresses to some kind of policy threshold. So some value which people, that could be the agencies involved, it could be users, some kind of number that people are comfortable with. That's what we would call our threshold for distress. We compare it. In case our calculated value exceeds the threshold, exceeds the maximum allowable value, we say the design has failed. We go back, we change our trial section. That's also not straightforward, and in subsequent lectures we will talk. In fact, the next lecture, which will be on the topic of design optimization, we will have a discussion on how exactly we can update our design. But we basically go back, we update our design, repeat the entire analysis, keep checking. Has the distress exceeded the allowable level of distress? If it has, keep doing it until the distress falls below the allowable level of distress. That final design then, where the distress is below the allowable distress or the maximum allowable distress, that we call as the final design. So what you'll notice here is, in the design, within design is contained at least one analysis step, typically 4, 5, even 6 analysis steps. So the reason we took so much time and have been repeating concepts of analysis so much is because you have to be the master of analysis in order to be able to do design properly, at least in the mechanistic empirical design philosophy. Okay, so in module 2, we did analysis using classical methods. Classical methods were methods where, under a set of assumptions, and as we saw later, there were questionable assumptions, but under a set of assumptions, we have a closed form solution to a differential equation. The differential equation, of course, Sophie-Germain equation with a correction for Winkler foundation, that is the governing differential equation for JPCP. So we saw Westergaard's theory, we saw some updated theories. We saw the Freiberg theory, which is actually based on Timoshenko beam theory. So we saw the Freiberg theory for analysis of dowels. All of them gave us some nice closed form solutions, which we could implement maybe by hand, maybe on a calculator, at most on a spreadsheet program. But there were several limitations of these classical methods. The limitations are really a result of all the assumptions that they made, namely that the slabs are very large, that is, the only joints which are affecting the distresses or affecting the stress or deflections in the slab are the joints which are just near the load, and the other joints are very far away from the load. That was the major assumption. That's actually the biggest assumption that leads to quite a lot of underestimation of deflection and overestimation of stresses in our calculations. Other assumptions were the type of the tire footprint. So the assumption that the tire footprint is either a circle or a square, which is not at all reasonable for realistic applications. And then you have further complications. Those complications could come out in the form of the subgrade, the behavioral subgrade, certain nonlinearities, etc., etc. So because of all those limitations and because of the growth of digital computers since the 1930s, since the 1990s, so roughly 30 years ago, because of that, over time, and the analysis of rigid pavements has moved away from classical methods and has gone towards using numerical methods or the finite element method. Now, again, I cannot teach you finite element method in 2 or 3 lectures. This is not a course on FEM. I do recommend all of you in civil, or if you have any mechanical engineering background, do take a formal course on the finite element method. There are lots of intricacies in that method. But the fundamental idea for the finite element method is that first of all, we are not looking for an exact solution. In analytical methods, we are looking to get an exact solution to a differential equation. In the finite element method, we give up the idea that we get an exact solution. We hope we get a solution such that there is an error, but the error can be made small using some relatively simple techniques. Those techniques, which is basically based on local support, we learned about it in those earlier lectures, so you want to go back and review those if you need to. Another assumption which comes into the finite element method is we are no longer solving our solution. That is, we are no longer trying to solve whatever value we are interested in, which we call the degrees of freedom. We are no longer trying to solve it everywhere. We are solving it only at a discrete set of nodes, and those nodes in turn are connected by elements. And we say that the solution at the nodes are calculated. The solution in between nodes, inside any element, is based on some simple and arbitrary interpolation. So, and those functions for interpolation are called shape functions, is based on an arbitrary interpolation of values between the nodes. The end result of the finite element method is that instead of trying to solve a differential equation with some fairly complicated looking boundary conditions, we actually end up simply solving a series of algebraic equations. Now, when I say series of, I don't mean 1 or 2 equations. There are thousands, tens of thousands, lakhs of equations which have to be solved. So we have a very large number of equations. But the good news is digital computers are very good at solving these type of equations. So you will, I think many of you would agree with me, the module 3 on finite elements was actually the most complicated module. But at the very end of that module, in the final lecture, I showed you that it's important for you to understand the finite element method, it's important for you to understand the formulation, but at the end of the day, we always resort to a computer program to do those calculations for us. And so I showed you ISLAB 2000, which was a computer program, ISLAB 2005 actually, which was a computer program which was developed specially for the mechanistic empirical analysis of rigid pavements as part of AASHTO's MEPDG procedure. So coming to AASHTO, we then came to module 4. Module 4 was finally on mechanistic empirical design. Mechanistic empirical design, I emphasize, is a technique, of course, but mechanistic empirical design is a philosophy. It is not an improved version of the old design methods, which were empirical design methods. It's actually a completely different method built on a completely different philosophy. And the philosophy is as follows: that for any pavement, we can calculate its mechanistic responses. We'll talk about this once in a second, but for any pavement, we can calculate the mechanistic responses through fundamental physics. And by physics, I basically mean solid mechanics, whatever all of you learned in your strengths of materials classes. It's a little bit more complicated in terms of the mathematics, but it's essentially the same idea. So the mechanistic part is where we calculate the stresses, deflections, and strains. That's fine, but then we also analyze pavements using fatigue theory. If we were only interested in the stresses or the deflections or the strains, then we would actually be using LRFD theory, and LRFD theory does not fully explain the behavior of rigid pavements, or of actually pavements in general, but rigid pavements for this class. So we have to use fatigue theory to explain the failure mechanism, and in fatigue theory, we actually have to take our stress, and from that stress we divide the stress by the strength, and we get what is called the stress ratio. From the stress ratio, we use another another equation which is called an SN curve. That is the number of allowable repetitions to failure at a given stress level or at a given stress ratio. That's what is called an SN curve. It's sort of the main constitutive model of fatigue theory. So we get this SN curve, and from the stress that we calculate the allowable repetitions. Then we look at our traffic information, we calculate the we calculate the actual number of repetitions. We divide the actual number of repetitions by the maximum allowable number of repetitions for each stress ratio, for each stress level, and we get a fatigue damage. The fatigue damage is added up for all climate loads, for all climatic conditions, for all external loads, which are vehicular loads, and we get the cumulative fatigue damage. The cumulative fatigue damage is the final number that we can possibly get through a purely mechanistic process. But cumulative fatigue damage, as we talked about, it's a number. It's a mathematical number. It doesn't actually mean anything in practice. What matters to us as engineers is not the fatigue damage. It is not really a thing you can see or something you can measure. What matters to us in practice is the distress. We care about, for JPCP, we care about fatigue, cracking, we care about faulting, we care about IRI. For CRCP, we care about punch outs, we might care about crack width, etc. So what we want is we want to be able to convert this fatigue damage or cumulative fatigue damage into one of these distresses. And that process uses an empirical function called a transfer function. That is the empirical part of mechanistic empirical design. So the mechanistic part of ME design ends at the calculation of cumulative fatigue damage. The empirical part is where the cumulative fatigue damage is converted to some distress of interest, and that's where this that function that does it is called a transfer function, which is purely based on empirical calculations. That is based on data which is collected from in-service roads. And so this whole process is called mechanistic empirical design, where we are trying to predict the performance of the pavement using both mechanics as well as some empirical information, as opposed to the previous design philosophy, which is purely empirical, where we do a lot of very expensive road tests and try to use that to predict pavement performance in the future. Okay, so that is a long introduction. What we've been looking at for the past several lectures is actually not ME design in general, but we've been looking at one implementation of ME design, which is in the United States and in several other countries, the AASHTO MEPDG, that is the Mechanistic Empirical Pavement Design Guide. And which today is the modern brand name for it is AASHTO Pavement ME. I'm kind of using them synonymously at this point. Although there are some slight differences, but largely I'm taking them to be synonymous. So what we saw in the several lectures was we saw particularly how AASHTO ME takes into account traffic, how it takes into account climate, and we saw in one lecture on linearization how it combines the effect of traffic and climate to significantly reduce the uncertainty as well as the number of simulations that have to be performed. Because one aspect of mechanistic empirical design is if you're using solid mechanics, we are going to be doing a lot of calculations. So we need to somehow reduce the number of calculations so that we don't sit for days to get one design out of the design procedure. Okay, now based on that, in the previous lecture, I showed you how we combined all this knowledge. So all this knowledge of analysis, finite element analysis, all this knowledge of transfer functions and fatigue damage, etc. All of these topics which we've been learning over time. The previous lecture, we actually brought all of it together, and I showed you how MEPDG calculates or designs JPCP. I promised to you at the end of that CRCP, the analysis of CRCP follows very closely to the analysis of JPCP, but at the point of design, the two diverge from each other. So what I wanted to show in today's lecture, which is going to be the one of only 2 lectures in our entire course, which is going to be exclusively on CRCP. So in today's lecture, I want to take you through how the AASHTO pavement ME procedure is used for the design of CRCP. So the lecture objectives are, I actually want to talk about one factor which I did not talk about in the previous one, but it is important to know. I wanted to describe something called wander. It plays a role both for CRCP as well as for JPCP, so it is appropriate in today's lecture. I wanted to formally define a term called wander and how it is accounted for in MEPDG. Later on, we will see in the Indian practice, which is IRC 58 for JPCP and IRC 118 for CRCP, we will see how wander is accounted for in the Indian practice. But I wanted to show you in AASHTO ME, how do the AASHTO pavement ME, how do they account for wander and what is wander? And then we'll go into the full analysis, full consideration of how the MEPDG does design of CRCP. Okay, so just as a brief reminder, this is the overall design procedure. This is the philosophical way that any ME design procedure works. We start with some inputs. The inputs are some materials, some traffic, some climate, some amount of variability if you want to consider it, and eventually a trial structure. So the structure is not just the thickness of the surface layer, because that is basically what we get in most of the empirical designs. It is the thickness of all the layers, it is the material properties of all the layers, it is the location, etc., etc. So that's what we call a trial structure. We use a structural response model, which in MEPDG in the previous lecture we saw the structural response model is some artificial neural networks which were developed by running several runs of ISLAB. So please go back to the previous lecture if you want a review on the artificial neural networks. So this structural response model takes in these inputs and calculates structural responses, that is stress, strain, as well as displacement. That is done using these, that is the mechanistic part of it. It can eventually be converted into fatigue damage or differential energy, whatever is the value that has to be considered. These structural responses have to be converted into pavement distresses using these transfer functions. That is a purely empirical concept. Then we add some reliability, which we'll talk about 2 lectures from now. So just hold off on this reliability for a second. We apply some amount of reliability and we check our pavement performance compared to some failure criteria. If it does not pass the failure criteria, repeat, get a new trial structure, keep going until you pass. Once you pass, that's called a final design. So this was generally how all mechanistic empirical design works. What you also want to recall is that in mechanistic empirical design, we actually have to do quite a lot of effort to characterize traffic. It is much more complicated than what we do for empirical designs. There are basically 4 types of axles that we now have to consider: single, tandem, tridem, and quad axles. Quad axles are rare, so I won't really talk too much about it, although I will give you a little bit of discussion on it. So single axles are basically axles which consists of one axle. Thus, you can, each of these, by the way, can be single wheel or dual wheel. Generally in pavement design, we are interested in buses and trucks. We're really not interested in cars because generally the fatigue damage from them is negligible. In fact, it's so negligible it might fall below the endurance limit if the concept of endurance limit is being used. So we have these single, so each, in most practical cases, we always have dual wheel. That is, we actually have 2 tires on each side. So a single axle is just one axle. A tandem axle is where you have another axle, but the distance between these is relatively small. In Indian practice, that is not more than 1.8 meters. And then you have a tridem axle where the overall outer distance is not more than 3 meters. So this is to be less than 3 meters, this is less than 1. So it's not more than 3 meters. So that is what we call a tridem axle. So in all cases, we're only talking about dual wheel. So a single axle dual wheel, which sometimes we write as SADW, it consists of 4 wheels. A tandem axle dual wheel consists of 8 wheels, double of that. And a tridem, we write it as TR. A tridem axle dual wheel consists of 12 wheels. I'll let you calculate what a quad axle dual wheel would consist of, but it's very rarely used. So given the fact that we have all these wheels, where do we place them? If you recall Westergaard's theory, it is very, very important where we place our loads. Depending on the position where the loads are placed relative to the edges, it can have a significant effect on stresses. So in pavement ME, each of these axle configurations is accounted for by counting a different number of wheels. Now, one thing to keep in mind is the reason we actually counted this different number of wheels is because the axle overall is going to carry some load, 80, 100, 200, 250 kilonewtons, whatever the number is. But the axles are individually going to be carrying a certain amount of load. What we actually are concerned with, what is the load on each wheel? So we have actually done this calculation where you basically take the total axle load, you divide it by the number of wheels, which we get from the slide, and then that gives you the load on each wheel. What pavement ME does is, for bottom up cracking, it has the following load locations where it places the load. Now, as a reminder, if this is the slab, then the critical load location is basically here. That if this is the direction of traffic, which I'll draw over here, if this is the direction of traffic, then the load is actually placed in the middle of the slab such that the axle is exactly at the middle. That is for a single axle. So when we have a single axle, if you just look, so this is basically my plan view, and these figures which I want to discuss in a second, these are elevation views. So in the elevation view, if we are interested in this point, this little green point over here, if you are interested in this point, that our critical load is going to occur at that point. For that, if we have a single axle, we place the axle exactly over that point in the vertical plane. Of course, horizontally, we do place it at some lateral placement. That's basically wandered. We'll talk about that in a second. But we place the single axle exactly at that point. Now, if we have a tandem axle, then what Ashto Emid says is you actually place the load at two locations. You look at one condition where you have one tire on exactly above the point of interest and one which is next to it. So you have to put one of the axles exactly on the above the point of interest, and the other one you can place either to its left or to its right. So that's what these two cases are. If we have a tridem axle, for a tridem axle, it's actually quite interesting. Again, we are interested to calculate the stress at this critical point, which is shown in this green circle over here. So for a tridem axle, what the guidelines from MEPDG say are that if we can have basically three cases. You can have the three cases are each of the axles can be exactly above the load in consideration. If we have a situation where the one of the outer axles is placed directly above the load, so this is an outer axle, this is an outer axle. If one of the outer axles is placed directly above the load, then the other outer axle is to be neglected. That's what this X cross mark on these means. That is, in these two cases, not the middle case yet, but in these two cases, if we are placing the outer axle exactly on top of the load, then this basically becomes tandem axle dual wheel, but with the load on the wheel as considered using this calculation. So for example, if the total tridem axle load is, for example, 240 kilonewtons, it's tridem axle dual wheel. So tridem axle dual wheel has 12 wheels. So the load on each wheel is basically going to be 240 divided by 12, that's 20 kilonewtons, right? And so what we will consider is, in these two cases, we put 20 kilonewton load. Actually, we put an 80 kilonewton axle, which is above this point, and next to it, we put another 80 kilonewton axle. Similarly, 80 kilonewton axle above the point and another 80 kilonewton axle. The third 80 kilonewton axle we disregard, unless the middle axle, so the inner axle. If the inner axle is exactly above the point of interest, then we have to consider all three axles. So for tridem axle, we actually have, so for single axle, you only have one loading configuration. For tandem axle, we have two loading configurations. In tridem axle, we have three loading configurations, in one of which all three axles will be considered, and in two of which only two of the axles will be considered. For quad axles, which are again very rare, so I'm not going to really go into too much detail, but for quad axles, the idea is if you have this configuration where you have one of the outer lower axles is placed directly above the point of interest, then we disregard the opposite side, the outer axis. So if you have these two axes which are placed here, we ignore these two and the ends here. Similarly, if these two are placed here, we ignore the other two over here. If on the other hand, one of the inner axles, so if not the two outer axles, if one of the two inner axles is placed on top, then it's effectively treated as though it's a tridem axle. That is, we ignore the outermost axle in that case. So these are the cases which are used for quad. This is for bottom-up cracking. For top-down cracking, it's quite similar for top-down cracking, but in top-down cracking, the wheel base. So the wheel base is basically, if I draw this truck, we had talked about this, but let me remind you, if I had this truck, we have one wheel here, we have another set here. The total distance, outer distance between the wheels is called the wheelbase. So for top-down cracking, the wheelbase of the trucks has to be considered, and it can be a short, medium, or a long wheelbase depending on the type of truck, and the appropriate set of axles therefore has to be analyzed. The main idea for top-down cracking is you have to have your loading configuration like this, that you have to have an axle here, another axle here, and then another axle here, and this is another slab. So you have to have more detailed knowledge about what is actually the wheelbase, what is this distance, what is this distance. You have to know what those distances are. So it requires a detailed knowledge of axle configurations. Some default values are also known, but generally the analysis of top-down cracking is more complicated than the analysis of bottom-up cracking, for this reason that we have to have more detailed knowledge about the wheelbase, which is at least not very important when we're doing bottom-up cracking. Okay. Finally, for faulting, I had mentioned for faulting, the main idea is in faulting the critical location. They will have maximum deflections is actually at the corner. So what we do is we actually place our axle at the corner such that this is a dual wheel system. So one of our dual wheels is actually at the corner. So this is again the plan view. If I look at the elevation view, then it looks as follows. So if you have a single axle, then you just place it here. for single axle and our point of interest is the corner, we just place the single axle exactly at the corner. If we have a tandem axle, then we place one of the tires on the corner and the other which is in the interior of the slab. If we have a tridem axle, then we place the outer axle on the corner and then the other axles come inside. If you have a quad axle, interestingly, the recommendation of Pavement ME is treat it exactly like a tridem axle, that is, ignore the last axle and just consider these three axles. So these are the axle configurations which are used for faulting. So what I showed you is what are the axle configurations which are used for bottom-up cracking, what are the additional things to keep in mind for top-down cracking, and then what are the axle configurations to be used for faulting. So now you know where exactly the load has to be placed in order to do the analysis. Okay. Now this was where this location of the load which is being placed is actually along the longitudinal location, that if this is going to be the direction of the traffic, we are saying where to place the load in this longitudinal direction. But we do have another direction which sometimes we call the transverse direction. So if this is the traffic direction, sometimes we call this as the transverse direction, sometimes we call this as the lateral direction. So we have to also know where do we place the load in the lateral direction. This is particularly important, as I showed over here, for when we're looking at bottom-up cracking, where we have to be very considerate of what this distance is. What is the distance from the edge, which is the longitudinal edge, up to the wheel that we are considering. It is an important number that we have to take into account. The stress is affected quite severely depending on where it is. I'll show you that in a couple of minutes. Okay, so one thing to keep in mind, one option, as you saw previously when we went to our lecture on linearization, that lateral position which I talked about was exactly 525 millimeters. It was a fixed value. So that was done for purposes of linearization. In theory, we could do it for all other cases that we're looking for, that for every traffic configuration that we have, we can just put it at that fixed location, which was again from this edge, we could just put all our loads at 525 millimeters. The problem is that vehicles are driven by humans. They do not actually, the wheel is never actually going to exactly follow what is called a wheel path. So the wheel path is never going to be exactly the same. Instead, what happens is there is an average wheel path the vehicle takes, but individual cars will also go around that wheel path. That laterally, the vehicles will be moving a little bit left or right along some mean wheel path. So the wheel path, which I can represent with the letter X, it is usually assumed to be a randomly distributed variable. Particularly, it's assumed to be a normally distributed random variable. And the normally distributed random variable has a variance of sigma square and a wheel path of mu. And in that case, the probability distribution, this is not CDF, by the way, this is just the PDF, the probability distribution of the wheel path, if we assume it's a normal distribution, which is generally the assumption we make, if we assume it's a normal distribution, then this is what that normal distribution looks like. Where again, sigma nu is what is this mean wheel path or the average wheel path. Sigma is the standard deviation of the wheel of the lateral position of the wheel about the wheel path. This the phenomenon in which vehicles do not follow an exact wheel path, but rather wander a little bit left and a little bit right, but still within the same lane. That's an important point, within the same lane. They wander a little bit left and a little bit right within the same lane. This phenomenon, which has been observed quite widely, is called wander. Okay, and in the United States, the observation has been that the standard deviation of the wander is 525 millimeters. This, by the way, if you recall, was the exact position where we put our so-called reference load during linearization. So I didn't explain to you then where that number comes from. This is where the number comes from. On average, as per US data. Now, India, this whole concept of wander actually doesn't work. So we'll see that later. But in the US, for US conditions, the mean of wheel path is actually 525 millimeters from the longitudinal edge. And that's why in linearization, we place our reference load at that point. It has also been observed that the standard deviation is 250 millimeters. So generally, if we use the concept of 2 sigma, that if you use nu plus or minus 2 sigma, basically accounts for almost everything. So 525 plus 250 into 2 or minus 252, that's generally the range. Somewhere in that location, we expect to find our load. And that's quite a large location. So that goes all the way, that's basically about from 100 mm to 1 meter. So that's quite a lot of distance that the vehicle can be in. So there is quite a lot of variation in the exact location of the axle from the edge. As I'll show you in the next slide, this is actually very important to consider, especially for rigid pavements. It is very important to consider because depending on the distance from our from the lateral position, so depending on the distance of our tire from the edge, from the longitudinal edge, this is what we call a lateral position. Depending on this lateral position, the stress changes dramatically. And if stress changes dramatically, the fatigue damage will therefore also change dramatically. How dramatically? Here is an image. Again, I got this from the MEPDG documentation. So here is the load location. This is, by the way, in inches because the documentation is inches. Just for those of you who don't know, very rough. The exact way to do it is that the value in millimeters is the value in inches into 25.4. It's not unusual to just ignore this 0.4 and just do it into 25. So if you just want to get a rough estimate of what these numbers are in millimeters, just multiply it by 25. Okay, so what this figure shows is as follows. On the x-axis, we have the load location from the pavement edge. This is that lateral position which I just mentioned. So this is the lateral position from the longitudinal edge. So it's, if this is the direction of traffic, this is basically what this is showing. On the right hand side, on the y-axis, what we have is the relative fatigue damage. Now, what is relative fatigue damage? That is, if the load is placed exactly at the edge, the fatigue damage is mapped to 100%, and if the load is placed elsewhere, the fatigue damage is divided by that fatigue damage. So relative to the fatigue damage at the edge, which is mapped to 100%, what is the fatigue damage at other locations? What you see, it's quite interesting. There is a dramatic drop off. As you get even this 2 inches, which is 50 mm, as you get just 50 mm from the edge, if you just 50 mm away from the edge, what we see is that you go from 100% of the fatigue damage to around 50% of the fatigue damage. So in a small distance of 50 mm, which is not much, around this much, in that much of a distance, your fatigue damage can reduce by half. And as you go further out, as you go further and further away, you see the fatigue damage drop very, very significantly. In fact, to a distance of around 150 mm, which is 6 inches, approximately 6 inches, to a distance of around 150 mm, it falls to something of the order of 5% of the total fatigue damage. So just a distance of 150 mm, which is not a very large distance at all. It's less than the stride of a foot of one step that you take. In just that much, your fatigue damage can go from 100% down to around 5% in that tiny distance. This 150, by the way, I just want you to commit to memory temporarily. The Indian practice for consideration of wander actually puts a very large emphasis on this one particular value of 150 mm. So we'll talk about that much later, several lectures later. But I want you to see this particular thing. So basically, depending on where I put my load location, my fatigue damage is going to vary significantly. How do I take this into account? So previously, when we were doing all our calculations, we were simply placing the load at the edge and we were calculating the fatigue damage. But as it turns out, based on this data which I'm showing you, that approach, the result of that approach is actually an overestimation of our fatigue damage, because fatigue damage is dropping off so dramatically. If we put 100% of our loads exactly at the edge, we are significantly overestimating fatigue damage, because in practice, 100% of the loads are not at the edge. Okay. So in theory, the wheel can be placed anywhere in the slab with a probability specified previously. Then what that means is, then what I can do is, I can place, at least in my numerical model, I can place my load anywhere I want. Anywhere on the pavement, I can place it wherever I want. I can calculate a fatigue damage, and I get a probability from here. I get the probability of the load being at that point. So I can get at each of these points, I can get a fatigue damage, I can get the probability of the fatigue damage, and I can multiply it with the fatigue damage. So for example, if I'm interested in doing it, let's say at every 50 mm, every 25 mm, I might have 10 to 20 different load positions. So I put the load position at maybe 10 or 20 different positions. I calculate what is the fatigue damage at each of those positions, and for each of the load levels and each of the climate, which gets into where I'm coming from. So I can put the load at each of these positions. I can calculate then what is the fatigue damage, and then I simply multiply the probability of that position with the fatigue damage, and I will end up getting the average fatigue damage for taking into account this phenomenon of wander. That is basically the area of this curve. As I've kind of highlighted over here or alluded to, that's basically the area of the curve. So we can basically construct this curve that we place the load at each of these positions, we calculate the fatigue damage, and then we calculate the area under the curve. That basically will give us the weighted fatigue damage taking into account this wander or this lateral placement. So that is true, and so basically we want to calculate the area of this curve. There are two ways to do it. This you learn a little bit more if you take a finite element class on this, but the first approach is as follows. We want to calculate the area of this curve, but we want to calculate it obviously very accurately, as accurately as possible. So approach one, we can choose a very large number of points. So maybe at every 50 mm, at every 25 mm, maybe at every 10 mm or 5 mm, we choose a large number of lateral positions. We place the load, we run our finite element model, we get the fatigue, we get the stress, we get the fatigue damage. You do it basically, so this is the curve. You place the load at very closely spaced points. You construct this curve and you calculate the area of the curve accordingly. The area could be calculated using, for example, something called the trapezoidal rule, which is a numerical method for integration. That's one approach. The other approach is to actually use some different technique which is called Gauss quadrature. So again, this is not a finite element course. I cannot teach you everything about Gauss quadrature, but let me tell you what happens, and the justification of it you probably actually learn on a class on your own. So let's go back here. So this is basically what our curve looked like. What the idea is that we can instead of calculating the fatigue damage at many points, the problem with calculating fatigue damage like this, the problem with calculating fatigue damage at a large number of points is that that's a lot of simulations. If you've been following me from the lecture on linearization, we do not want to perform millions and trillions of calculations. It's just too time consuming and too computationally intensive. We want to reduce the number of simulations. So if we use approach one, which is using the trapezoidal rule, to get an accurate estimate of the area, we will have to conduct a very large number of simulations. Instead, what we do in approach 2, which is using Gauss quadrature, we actually place the loads at some, let me use the quotation marks over here, at some special points. And these special points, the technical term for this is basically Gauss points. So we place the load at some special points which are called Gauss points. And using the principle of Gauss quadrature, then we can get an extremely accurate estimate of the error using a very small number of evaluations. In particular, as I'll show you, Pavement ME will actually just use 6 evaluations. So instead of doing an evaluation for a very large number of points, 10, 20 points or more, you just do an evaluation at 6 points and you can get a very accurate estimate of the area using this particular technique called Gauss quadrature. We do not have time to go into details on what is Gauss quadrature. I encourage you to take a formal class on finite element methods if you want to know Gauss quadrature. But for now, just understand Pavement ME uses this approach that for lateral position, it actually places the loads laterally at certain points which are called Gauss points. It uses 6 points. It does it at 6 different locations, and from there it gets a very accurate estimate of what the error is. This, by the way, is done separately for bottom up and top down cracking. Why? Because as I showed previously over here, for bottom up and top down cracking, the position of the loads themselves, not the lateral position, but the longitudinal position of the loads is separate. And so this whole analysis is done separately for bottom up and top down cracking. Okay. So as I said that in this approach of Pavement, approach 2, where we use Gauss quadrature, 6 points are used in the evaluation. Why 6? Okay, the answer is as follows. So again, we have this curve. The curve is basically for lateral position, or maybe you can call it wander. This is wander, and this is the fatigue damage. The idea is as follows. For the first 40% of the wander distance, it is approximated using a 7th order polynomial. So as you see over here in this figure, which is taken directly from the documentation, the first 40% might maybe come up to this point over here. So this is maybe the first 40%. You see that this is a very nonlinear curve. So this is actually approximated using a 7th order polynomial. I'm not going to go into details, but basically you can exactly get the area of under a 7th order polynomial using a 4-point Gauss quadrature. So that means for the first 40%, we evaluate the fatigue damage at 4 special points, which are Gauss points, and we will get an extremely accurate estimate of the area using these 4 evaluations. The remaining 60%, as you will see in this figure over here, the remaining 60% is actually quite flat. It doesn't vary, it's certainly not as non-linear as the first 40%. So the remaining 60% is relatively flat. You do not need such a high order, 7th order polynomial to approximate it. It's sufficient if you just do a 3rd order polynomial in the approximation. Again, without going into details, a 3rd order polynomial, which is a cubic polynomial, it can be very well approximated. It can be actually be exactly, not even approximated, it can be exactly evaluated using 2-point Gauss quadrature. So in this, so this is the first 40%. In the remaining 60%, we just evaluate the fatigue damage at these 2 points, and we get an extremely accurate estimate of what the area under this curve is. Thus, the fatigue damage is evaluated totally by placing the load at 6 lateral positions, which are these 6 Gauss points. This is done for every axle configuration, for every combination of load and climate which comes out of linearization, which we talked about in the previous class. As you can see, what we have effectively done is we have increased the number of evaluations by a factor of 6. That is the price that has to be paid. When we get to the Indian practice in IRC 58, we'll see that we actually eliminate this through, well, we'll talk about it over then, but we end up eliminating it by severely reducing the amount of traffic. So we make even more approximations and even more assumptions to this. But sticking to pavement ME, basically this issue of wander, just this one phenomenon alone has increased our computational load by a factor of 6. So this is the challenge in mechanistic empirical design. The number of evaluations you have to do is just massive, and every additional variable you take into account blows up the number of evaluations that you have to perform. Anyway, so that was on lateral position and that was on wander. That's just some topics I wanted to cover that applies equally to JPCP as well as to CRCP. So now let's take the remaining part of the lecture to talk about CRCP design. CRCP analysis is very, very similar to JPCP analysis. Everything I discussed previously, be it plate theory, be it iSlab, be it the effect of joints, analysis of joints, be it linearization, climate consideration, traffic consideration, etc. Everything applies equally to CRCP as it did for JPCP. JPCP does start to vary a little bit when we actually have to do design, and we'll talk about it right now. Okay, so here is the general procedure for CRCP design. Again, I'm getting this out of NCHRP 137A, which is the original project which developed the AASHTO Mechanistic Empirical Pavement Design Guide. Free to download, just Google NCHRP 137A, you'll find a link and you'll be able to download a pretty large folder. It's several thousand pages of discussion, so it's quite heavy actually to go through it, but I've gone through most of it and I'm just giving you what the important parts are. So here is the MEPDG CRCP design procedure. The first step is what you would expect. You have to select a trial design. So layer thickness materials, presence of shoulder, that's whether it's tied or untied, construction. One new thing, so all of those previous ones are identical to JPCP. One new thing is reinforcement. This we did not have in JPCP design. In JPCP design, we basically almost always have dowels, so we assume that there is dowels. Reinforcement, however, now just recall in CRCP, we do not have any joints. So we start the CRCP at some point, but we don't have any joints. So this basically goes on for the entire length of the road. But inside the pavement, we have a mesh of steel. So in JPCP, the steel is only present at the joints. In CRCP, the steel is present everywhere. We have this main reinforcement steel, which is this is the traffic direction. So we have this main reinforcement steel and we have this primary reinforcement. We also have the secondary reinforcement, which is perpendicular. The purpose of the secondary reinforcement is simply to make sure the primary reinforcement does not move. But as such, the secondary reinforcement is, as far as design is concerned, does not actually have any contribution. So we are very much concerned about the primary reinforcement. So that's an additional input. We'll talk about what exactly that input is in a second, but we have to provide some inputs related to primary reinforcement. That is part of our trial design. We provide some site-specific inputs, climate, foundation, traffic, identical to JPCP. I won't repeat it. We put in some performance criteria. What is the performance that we are interested in? And in this case, if you recall in the previous lecture for JPCP, we were interested in 3 distresses. We were interested in fatigue damage, or we were interested in cracking, fatigue cracking. We were interested in faulting, and we were interested in a composite value called IRI, which you could say is a measure of smoothness. For CRCP, we are actually interested in only 2 things. As per the pavement ME design, we are interested in punch outs and we are interested in IRI. So IRI still makes a comeback. So we have to set some performance criteria. Punch outs, by the way, is usually shown in the number of punch. So a punch out, in case you forget, so if you have CRCP, in CRCP you're going to have a regular series of cracks, transverse cracks which are forming. They're natural, they're very tight cracks, so they do not allow any moisture to ingress, or no significant amount of moisture anyway. They do not allow any significant moisture ingress. They're very smooth to drive on. So although they are cracks, they're not actually distresses. The distress is actually when we start having some longitudinal cracks forming, and so then you have a piece of the pavement which is separated from the rest of the pavement, and then under a heavy load it will literally fly out, and hence the name punch outs. So punch outs is what we're very interested in. We are also interested in IRI. So our performance criteria has to be set for punch outs as well as IRI. Punch outs are measured in as number per kilometer or number per mile. So the number of these punch outs which occur per mile or per kilometer, that is how we measure the severity of the punch outs. Okay, we also have to put in some reliability. Again, I'll explain reliability a little bit in later lectures. So those were all our inputs. Now we come into this analysis box, and what's happening in analysis is that punch outs have to be calculated. To calculate punch outs, we have to make several calculations internally. We have to calculate the crack width. We have to calculate the load transfer. These are new concepts which we have not looked at previously. Previously, we didn't have any cracks in JPCB, so there was no crack width to calculate. There was no load transfer in the sense we have dowels, and the dowels are taking care of load transfer. What's happening in CRCP, however, again in CRCP, so you have this long pavement and you have these continuous cracks which are forming. Each of those cracks has a crack width, and as I said, the crack width has to be very, very small. So we have to be able to predict the crack width, one. We also have to be able to predict that depending on the crack width is actually going to determine how much load transfer we have across the crack. So in JPCP, load transfer occurs across the joint. In CRCP, the load transfer occurs across the crack. So we have to calculate, and it is a function also of crack width. So we have to calculate the crack width. We have to calculate the amount of load transfer which is coming for that crack width. Based on that, then we place the load. I'll show you where we place the load in a second. We place the load, we calculate the stress, we calculate the fatigue damage, and there we predict punch outs, which is actually very similar to predicting cracking. We'll talk about that later. So now we've predicted punch outs. We then also predict what is IRI, which in turn depends on predicting punch outs itself. And then that ends our analysis step. Then we go out into our design step, check that the predicted performance against design criteria at the reliability level. In other words, is the IRI less than the maximum allowable IRI? Are the number of punch outs per kilometer less than the maximum allowable number? If no, go back, choose a new trial structure, repeat. If yes, then that's a completed design. So that's the overall process that is used for the design of CRCP. So here again, let me illustrate to you what we're looking at. So this is a CRCP section. This is going to go on for a very long distance. Here we have the pavement edge. This is actually the center line of the pavement shown over here. As I said, that we will have roughly at every 1 meter, there will be a regular series of transverse cracks. These transverse cracks are not distresses. These are not distresses. They are meant to be there. They are a feature of CRCP. These transverse cracks have a certain width. The width is very small. Now, what happens is that a longitudinal crack forms. So we are supposed to have transverse cracks. We are not supposed to have longitudinal cracks. So longitudinal crack forms, and those longitudinal cracks are actually the distresses. So the transverse cracks are not distresses. The longitudinal cracks are the distresses. So we have these longitudinal cracks, and once a longitudinal crack successfully connects to transverse cracks, this area becomes a punch out. So the critical location that we're interested in, we actually place the load as follows. We place the tire we place it exactly at one of these cracks. So the crack is sort of our joint, although there are no joints in CRCP. We place our load at one of these crack edges, and we also place it right at the pavement edge or right at the longitudinal edge. Under these conditions, then the critical load, the critical stress is going to occur somewhere along this longitudinal crack. The location of that critical stress is actually where longitudinal cracking will initiate, and then longitudinal cracking will propagate accordingly. So this is basically how we do our MEPDG CRCP design. This is generally what we're looking at. So the load location, that's the most important thing to come out here. The load placement location in this case is as I've shown over here, on a transverse crack. There's no joint. On the transverse crack and exactly next to the pavement edge, that's our critical location. Okay. Now, once we have all this information, so once we know where the transverse crack is actually placed, once we know what is the load transfer across the transverse crack, which in turn is a function of the crack width. Once we have all that, stresses are actually calculated identically to JPCP. That, and generally we start with an assumption initially of 95% load transfer. So if we have very small crack width, as acceptably small crack width, generally we assume 95% load transfer efficiency, but that is also updated incrementally as the analysis goes forward. So the stresses are calculated identically to JPCP. That is, we use neural network A1, A2 and neural network B1, B2. Please go back to the previous lecture if you want a summary of what those neural networks are. The design of the steel, however, is highly critical. So that is one significant difference between JPCP and CRCP. We have to talk about the steel, which we generally don't talk about too much, the placement of the steel. So in JPCP, if you recall, if this is basically where I have this is my load. If this is my slab, I basically place the steel at a depth of h/2, exactly at half, and I allow a crack to form like this. That is not what happens in CRCP. CRCP, first of all, the crack width must generally be kept below half a millimeter. If it's more than half a millimeter, you are going to have significant deterioration in load transfer. But what I want to show in this slide in particular, this again is taken from the documentation. What this slide is showing, first of all, is what is the percentage of steel. Percentage of steel, as in structural engineering, is always shown as area of the cross section. So if we looked at the cross section of a JPCP slab, we would have these regularly placed steel bars. These are not called dowel bars. These are called primary reinforcement as far as CRCP is concerned. So what we do is, this is our cross section. We have this total cross section A. We can calculate the total cross section of the steel, which is AS. And therefore, the cross section of steel, the percentage cross section is always AS divided by A. This is identical to RCC design in structural design. So I hope all of you are familiar with this concept. What you see in this figure is, on the x-axis you have years, on the y-axis you have punch-outs per mile, which could be punch-outs per kilometer, you can just scale it. So this is punch-outs per mile on a particular section. And this, by the way, this is based on some numerical analysis, but is also based on some data which is actually collected using one of the LTPP sections. We talked about LTPP in an earlier lecture. Okay, so what we see here is, as the percentage of steel decreases, so percent of steel is decreasing, the number of punch-outs per mile, which is our main distress mechanism, it's growing significantly. It's actually growing exponentially. So when we have about 0.8% or even 0.65%, we had around 2 punch-outs per mile. When we had half a percentage of steel, it dramatically rose to around 15 punch-outs per mile, factor of 7. So what you can see is, the percentage of steel is actually very important. So we have to know how much steel to place. It's a choice. It's an engineering choice we have that determines how much steel we place across the cross section. Now, that's the amount of steel or the number of steel bars. The steel is also usually placed roughly 80 mm to mid depth below the surface. Recall, as I drew over here, in JPCP, the steel, which is the dowel, is always placed at h/2. That's basically a fixed position. Whereas for CRCP, the position of the steel is also a choice that we get to make. Generally, it is put from 80 mm to mid depth. Why? The closer to the surface, the tighter is the crack. So I remind you, as I mentioned over here, the crack width is very important to determine the amount of load transfer. The smaller the crack width, the more efficient load transfer you'll have across the crack. Not across the joint, there are no joints. The load transfer is across the crack. So we want to severely limit the crack width. The easiest way to control the crack width to make it tighter is to keep the steel close to the surface. The problem is, we can't place the steel exactly on the surface. We'll start having corrosion. We have to provide some cover, as we call it structural engineering. We have to provide some amount of cover. So generally, the minimum cover that's based on practice recommended is 80 millimeters. Of course, it can change based on local practice. There's not enough experience with CRCP to give more detailed values, unlike structural engineering for RCC design. So 80 mm to somewhere to half mid depth. So 80 mm to h/2, we place the steel. Generally, the idea is try to place the steel as close to the surface, but no more than 80 mm. Okay. Now, this transverse steel, which we call primary reinforcement, it is only the secondary reinforcement. So if this is my CRCP, this is my primary reinforcement or longitudinal reinforcement. Secondary reinforcement or transverse reinforcement, which is what I drew over here, it's only needed to tie the steel in place. It does not, at least from a design perspective, it does not really do anything to hold the cracks together due to the need for placing the steel properly. So it is very, very crucial that the steel is placed properly during construction. You can put any numbers you want in design, but it has to actually happen in construction. Because the steel has to be placed so carefully and at such a specific location, CRCP is usually built on a stabilized base. That our base is usually cement treated or asphalt treated, something which is solid so the steel does not move even a little bit during construction. And that is one of the things that makes CRCP quite expensive to construct. Okay, so once we do that, we have to calculate punch out. So once we've decided where we want to place the steel, and we do our analysis to calculate crack width and load transfer, and then we run our usual neural network analysis to calculate stresses, and from there we get fatigue damage. That's basically the mechanistic part of it. The empirical part of it is to calculate the punch outs. I already said punch outs are basically caused by longitudinal cracks. So the transverse cracks are not distresses. The longitudinal cracks are distresses. And so if we can predict the longitudinal cracks, we can predict punch outs, because punch outs are basically a result of longitudinal cracks. So the transfer function for calculating punch outs is very, very similar to the transfer function for any kind of fatigue cracking, in this case longitudinal fatigue cracking. So is this 105, this is punch outs per mile, so not the units. 105.26 divided by 1 plus 4 FD raised to the power of minus 0.38. Again, these are some calibrated values. These values can change. These are empirical functions. We might have different values for these. Here is what this particular one looks like. So we have damage over here and we have number of punch outs per mile. This is actually the original data based on which this equation was fitted. So as is usual, you see for a small amount of damage and basically 0 punch outs, there is a very large amount of data. Much less data as the number of punch outs kept increasing. That's also characteristic of transfer functions. We talked about this in an earlier lecture. We tend to have more data where we don't need transfer functions, where we have very little damage. We tend to have less data where we have a lot of damage. That's in the nature of how the data for transfer functions is collected. But it's basically this particular S-shaped sort of curve. At 1, so at fatigue damage of 1, it approximately corresponds to 20 punch outs per mile. Now, one more difference between JPCP and CRCP is the length of the slab. So, in JPCP, the length of the slab is what we decide. It's where we saw those joints. In CRCP, the length of the slab is actually the distance between the cracks. So, generally, some CRCP models additionally have some functions which quickly evaluate what is the slab size, what is the spacing between the cracks. It can be calculated, for example, using this quick formula, which is shown over here, again, from the NCHRP documentation. It's just something you should know, that even this length, it's roughly 1 meter. You can choose that as a fixed value, or you can just calculate it using the somewhat semi-empirical function. What you see here, it's also a function of the depth of the steel. So depth of the steel affects not only the crack width, it can also affect the crack spacing. So crack width, we can also directly determine the crack width. I showed you an equation of a transfer function to determine the crack width in the lecture on transfer functions. So please go back and take a look at that. Pavement ME further accounts for deterioration of the crack load transfer time. So initially it starts with an assumption of 95%. It does evaluate that over time that is going to decrease as the spalling in the crack and the crack width increases. So it does do that sort of incremental analysis. Okay. So that was the design of CRCP. That was the first of 2 lectures which we'll have, which are completely devoted to CRCP. We saw that to a large extent CRCP analysis, particularly the stress calculation, is very similar to JPCP. But around that is what is the size of the slab, what is the load transfer, and then what are the failure mechanisms and the transfer functions. There we have a lot of different variations. So I hope you saw that JPCP and CRCP are similar to each other up to a point, that is up to the analysis point, they're actually identical to each other. It's only in the design part where we have to start looking at aspects related to design where they start varying significantly. And the big thing about CRCP is the position and the amount of steel is a very important factor. That is the position above the surface or below the surface. That's a very important factor, which is not the case for JPCP and CRCP. Because the steel is so important, we generally always place it on some kind of a treated base so that we don't have any variation, any significant variation in the position of steel. I have been hinting for some time now that there's been something called reliability, and I kept showing it in various figures, but I have not been talking about what it is. So in the next lecture, we are actually going to formally introduce you to the concept of reliability, why we need it, and that with reliability then we will be able to close out one analysis loop of our mechanistic empirical design. So I see you in the next class where we'll talk about reliability. Thank you.